Hi, this is Vigyan Singhal from Oski Technology, and I want to talk to you about abstraction models and how abstraction models can transform the search space for a formal verification run and bring states which are distant closer to the reset state, allowing the proofs to converge. The state space for any formal tool is huge. Even if you have a design which is only 2 inputs, you start from the reset state in the middle. In one step you can get to 4 more new states, and then you take one more step, you get 4 more new states from each one of these states, and slowly you are faced with gazillion possible states. The space is huge. I mean, if you have a design which has only 30 flops in the entire cone of influence and the entire design for end-to-end proofs, then that's already a billion states. If you have a design which has 300 flops, which is still a very, very small design, that's already more states than the number of atoms in the universe. So the state space is growing exponentially, and it's hard to get a handle on the entire search space. The formal tools are doing a pretty good job in trying to traverse the entire search space, but there is a limit on how big a design you can handle and where the proofs stop converging. So what you want to do is you want to be able to use something called an abstraction model, which will allow which will transform the search space, bring the states which are distant closer to the reset states, and allow these proofs to converge much, much faster. And I'll show you an example today. So let's take a look at this design. It's a PCI Express design. It's the transaction layer of the design, and we're going to focus on the transmit side of the transaction layer of the design. On the right side of the design is traffic coming in from the application layer. On the left side, traffic is going to the data link layer. And of course there is the receive path also, but that's kind of interfering with the transmit path. And we want to verify this block, which is hard enough by itself. But actually what makes it even harder is, let's say inside the scheduler here on the top right side of the design, there is a small tag allocator design. And the only purpose of the tag allocator is to disperse unique tags to every new transaction that comes in. So the very first transaction comes in, it gets tag number 0. The next transaction gets tag number 1, tag number 2, tag number 3, and so on. And eventually the packets go through the system and start returning the tags. So the tags that this tag allocator RTL block is managing, they kind of get out of order soon enough. And the linked list, the nice linked list, it started with 0, 1, 2, 3, 4, up to let's say 1023 for 1024 possible tags. That gets out of order and sometimes becomes empty also. And what's interesting is that if you look at this interface for this tag allocator block, I mean, you have all these requesters coming in from one side of the design, many different requesters requesting simultaneously and asynchronously and concurrently, and the allocation is happening. And at the same time, tags are being returned by other packets in the system. And then moreover, I mean, you have the CPU which comes in and interferes in the middle and sometimes removes packets, removes tags, or resets all possible tags and so on. So lots of different action, lots of different things going on in the design, and they are simultaneously interfering with each other. Makes it really complex to prove a design like this. What we want to do is explore the corner cases of the design which happen when the linked list is empty. So you start with the linked list which is 1024 deep. At some point the linked list becomes empty, and then the bypass logic for the design kicks in. The bypass logic is never exercised until the linked list is empty, and the design becomes so much more interesting when the linked list is empty and harder to verify. But unfortunately, you won't get to that point with any formal tool, with any standard search, until at least 1024 cycles deep. And that's way too deep for any formal tool to go and traverse this without using abstraction model. So let's look at an abstraction model for this. So I'm going to make use of a symbolic tag ID called symtag, and it's going to be implemented by a constraint like this. And essentially what this is saying is that you pick any symbolic constant, and throughout any trace of the formal run, the symbolic constant has the same value. Now the formal tool is looking at all possible traces at the same time, so you'll exercise all possible values of the symbolic tag, but in any trace the tag will be the same. So suppose it's tag number 79, for example. So I'm going to build a state machine which is only 2 states, H and D. H denotes that the state machine has tag 79. D denotes it does not have 79. I start with the H, and if you come and ask me for a tag, I can give you either 79 or something else. If I give you 79, I move to state D. If I give you something else, I stay in a state H. I cannot say I'm empty because I have at least 79. When I go to D, I'm allowed to say I'm empty, and if I get 79 from D, I come back to H. So I have these additional properties which characterize the behavior of the abstraction model, and I have to assume these properties when I instantiate the abstraction model and replace the tag allocator RTL in the design. And the really cool thing that happens is that because I use this abstraction model, my search space shrinks in only one clock cycle. I'm able to hit all the corner cases where the tag allocator, the linked list is empty, and all the bypass logic corner cases are exercised. And that's the beauty of this abstraction model. A separate question is that how do I know my abstraction model is correct? So I have to do a second proof where I take the tag allocator RTL, compare it against the tag allocator abstraction model. The constraints that I use become assertions, and the assertions I use become constraints, and they just reverse, and the proof goes very simply because it's a much smaller piece of RTL than the transaction layer RTL. But using this abstraction model, I was able to cover the entire search space of the transaction layer RTL, which would have been impossible to cover otherwise. So that's the really cool thing about the abstraction model. So this is just one example. There are so many different kinds of abstraction models depending on the design you're verifying, depending on the complexity of the search space you have, depending on the checkers you're writing for that. So hope you'll get to use more of it. Thank you so much.